Okay, so if you have just the homogeneous equation, we don't have anything going in or out. As I say, it reduces down and you just do the usual. You use e to the lambda t times a column vector AB. Or if you're in, you got 3 tanks and all that stuff being ABC. Okay? And you get the eigenvalue problem. You solve for the eigenvalues. It tells you the ratio between A and B. So generally going to let A equal 1 and see what B is, or let B equal 1 and see what A has to be. So that's exactly what we did last time. If you haven't reviewed your notes, you refresh yourself. As I said, the equation's going to be just a little less symmetric. If these pumping rates aren't the same, but if you don't have any inflow and you keep the volume the same, you don't have any outflow, so the pumping rates pretty much have to be the same, don't they? Now, if you do have inflow and outflow with a constant volume, then you do have all of this, and you do have this non-homogeneous part of the equation. And this is where you get into variation of parameters. Okay? You try to use undetermined coefficients. It turns out that's harder to do for a system because of the way everything interplays between the two equations. But so it's much harder to try to use variation of parameters. I mean undetermined coefficients, which is really your first recourse when you're dealing with higher order equations with second order and higher equations with or without constant coefficients. Okay. Variation of parameters isn't that bad, especially if you understand how to derive it, which can be a little tricky because there's that one step that you got to have right before everything comes out. Turns out variation of parameters for systems, if you understand the linear algebra, and you understand enough linear algebra, at least if you reflect a little bit from last year, turns out that variation of parameters is actually pretty simple. Okay? For a system. Now that's as much as we're going to do with systems because of the loss of a credit hour on the course from last year. Okay? But there it is. Okay.